Good day, my name is Simon Morales from the Graduate School of Information Science and Technology at TOSAC University, and I will introduce our work for this year's International Conference of Pervasive Computing and Communication. The title of our research reads Acceleration-Based Human Activity Recognition and Packaging Tasks using Motif-guided Attention Networks. The contents of this presentation are as follows. I will start by describing the background of our research topic and give a brief introduction of our study scenario. After that, I will talk about our research approach and the methodology we applied. Then I will present the results accomplished from this research. And finally, I will talk about our future work on the topic. As we know, the emergence of Industry 4.0 has changed how manufacturing and logistics centers manage and improve their processes. With the introduction of the cyber physical system, or CPS, we can now better correlate events that occurred in the physical layer of factories, distribution centers, etc., by collecting data directly from the source and transferring it to the cyber layer. We can then use this data to design better strategies and methods of production. While it is easy to collect production and performance data from devices such as machines and robots and transfer it to the cyber layer, designing strategies without considering the human workers involved will lead to reduced results, and trying to include worker behavior without capturing relevant data is really tough. Collecting such data has become more plausible thanks to the increase of IoT technologies that are used in the industrial sector. Data such as worker location, motion, and physiological markers can now be collected using simple wearable devices. Our main research topic is to focus on transferring such data to the cyber layer and using artificial intelligence to interpret worker behaviors. Understanding said behaviors will allow for the creation of better strategies using workers as their focal point. One of the sectors that currently has struggled with creating such strategies is that of logistics and distribution. Given the increase and prevalence of e-commerce around the world, the number of delivery services available has augmented, as well as the variety of products that you can purchase and the size of packages that are delivered. All of these variations and combinations of factors create bottlenecks in the supply chain, especially when it comes to packaging products inside logistics centers. Here, many products from different sources are collected and repackaged to be shipped based on the customer preferences. This task is still mostly dependent on human workers, given our ability to grab and recognize products, even when so many of them exist. However, the activity is prone to errors and inefficiency inherent to the ability of each worker. For this, we analyze worker actions from data collected using wearable sensors in order to identify inefficient tasks and provide the logistics centers with relevant information to create strategies that will improve their packing lead times. Such an improvement will lead to an overall increase in the ability of the distribution supply chain. As for our particular study scenario, we have analyzed data from inside a real-life logistics center. Here, workers perform a set of operations that correspond to different packaging tasks, like picking items, packing them, and keeping track of the information on package data, reading labels. We asked some of these workers to wear a smartwatch in their dominant hand during the regular schedule and then collected some acceleration data from them. Here we can see one of the example of the workers in question performing the pack item operation. As for the goal of our study, we aim to identify the start and end times of each packaging operation performed during a working period. We look to provide each sample of acceleration data with a class label related to the operation performed, such as picking or packing an item. During one particular period, our workers perform several of the operations presented here. During a period, actually, no particular order is required, but obviously a certain pattern is followed, such as not closing the box before packing the items inside of it. The main challenge we face, however, is that recognizing complex activities from each other is quite difficult. While simple actions such as walking and running can be easily recognized by available machine learning technologies, recognizing complex actions is tougher. As we can see in this same example, a single complex operation can contain many smaller actions. Looking at the sensor data, we can clearly see the difference between open box and graph item. But when both of them correspond to the same pack item operation, it becomes difficult to find its similarities with other appearances of the same operation. We can see the complexity of trying to recognize the same operations when looking at separate working periods. In the example data for the pack item or attach label operations, we can see that the data looks different in each period, both in shape and length. This is because the smaller actions contain uncomplex operations vary for each period depending on the number of items and the size of each of them. That, combined with the work usability and other circumstances, makes recognizing packaging tasks really difficult for known machine learning models. For this challenge, we came up with the following idea. First, we found that for every packaging operation, there are some key actions, like stretching a tape when closing a cardboard box, or removing the protective film before pasting the shipping label, that are unique and representative atomic motions to their parent operations. In other words, it would be impossible to perform said operations without them. As we can see in the example periods, we can find such key actions from the sensor data even when other sections look totally different. That is because these key actions do not depend on the amount of items, their size, or the worker's ability. If we focus on finding such key actions directly from the sensor data and use them to better identify each complex packaging operation, we can solve the previous challenges. For this, we employ an attention-based approach. Similar to how attention in an image can highlight the stop sign when reconstructing the given sentence, of our approach can focus on attention in the relevant data segments that contain key actions that can help us identify each operation. The major problem with implementing this attention-based approach, however, is that training and attention mechanisms requires a large amount of data, and acquiring such an amount of labeled data from a real-life environment is difficult and costly. To solve this problem, we create a two-step approach. First, we apply motif identification to find 3 types of key actions for each operation. We find a start and ending motion for the operation, then a unique motion, and a secondary motion linked to the unique motif or key action. Then we pinpoint the location of all of these 3 actions in the rest of the sensor data, and we use the training data shape as well as the location of these key actions to guide our attention mechanisms training to be able to find automatically focus on the key actions that are relevant for each operation, by focusing on finding the extend label key action when trying to identify the label operation. Here we have an overview of our method. Our current method is divided into training and testing phases. During the training phase, we employ our two-step approach by pre-processing the sensor data and identifying 3 motifs during the motif identification algorithm. Then we train the motif-guided attention network with our motif-guided attention training. As for the testing phase, we just use the input of the sensor data and our train MGA-net model to identify each operation label from the testing period. Up until now, I have talked about how key actions are atomic motions that represent each operation. But how to select important or relevant motions as key actions? Well, key actions, like the ones I show here, can appear repeatedly on the data. This is also how we define motifs. We can say that the data structure that corresponds to scanning a QR code from the label corresponds not only to a key action of the read label operation, but also to a motif, since it appears multiple times in our training data. For all possible key actions that may exist for a particular operation, we selected to find 3 motifs for each one of them: a unique and supportive, a boundary motif, or in our example, scanning a QR code, separating the sticky label from the roll, and then scanning a barcode from the work order. Here is how the motif identification algorithm works. As input, we have the training data as a sequence of symbols. From this sequence, we first mine motif candidate seeds, then calculate the motif occurrence sequence for each of these seeds, and we select the top seed candidates as motif candidates. After this, we score the motif candidates to select a unique motif, then a supportive motif, and finally a boundary motif. Once the selection of these 3 motifs is complete, we output the motif occurrence sequences for each operation. To extract the motif seeds, we go to the first training period and then obtain as many symbol sequences as possible for each operation based on the motif size and available symbols. Motif sizes can vary depending on each operation. We can seed motifs from 2 to 15 symbols in length. After extraction, we scan the rest of the training periods in order to find other occurrences of the motif. For this, we calculate the similarity between the motif and the data window that is being scanned and create a motif occurrence sequence. This sequence has the similarity value of the candidate for each time window in the entire training sequence. An occurrence happens when the similarity between the symbols in the motif and those in the data are being above 90%. We then score the seeded candidates based on their number of occurrences in the training data and keep the 10 top motifs as motif candidates. Once we have all motif candidates, we start by scoring them in order to pick the unique motif. An example of a unique motif can be the scanning of a barcode from the work order. This action or motion is only performed during the read label activity, so it provides the model an assurance that when it appears, the read label activity is happening. The characteristics of this type of motif is that they usually are actions that are essential to the operation and appear mostly in the operation of interest. To score this type of motif, we consider the number of appearances inside the operation they belong to and outside of it. The bigger the difference, the higher the score. For example, the red and blue candidate motifs appear multiple times in the read label operation, but only the read label, the green motif appears only in the read label operation, making it the best unique motif. As for the supportive motif, a good example of separating the sticky label from the role. Right after the worker has scanned the order, then he has to take off the sticky label to place it in the box. Some characteristics of this supportive motif is the temporal link that it has to the unique motif, as it usually appears at a certain time interval from the unique motif. This time relationship gives the model better information about what the operation structure looks like. It teaches the network which actions come first and which come second. To score the unique motif, we count the number of times the pair of motifs appear together in the same operation, as well as how stable their time relationship is. The supportive motif can appear both before or after the unique motif while holding the same teleport distance. In this case, we select the light blue candidate as the supportive motif. The boundary motif, however, has a different type of purpose than the other motifs. With the unique motif and supportive motifs, we have a higher probability of identifying the correct operation. But in order to determine the start or ending time of the target action, we need to have information of what the boundaries look like. For this, we employ the boundary motif. Its characteristics are that it's seen as an action that marks the transition between operations. It usually appears in the beginning or the end of an operation. We score this motif mainly by its relationship with the boundary of an operation. The candidate closest to the edge and with the least amount of error is selected as the boundary motif. After selecting all three relevant motifs, we proceed with the network training. Here we have a structure of our motif-guided attention network, or MGANet. We base our model on the network structure called UNet. This network structure is known for its ability to segment sequential actions better than other traditional convolutional and even recurrent neural networks. On the original UNet structure, we have two paths on the encoder and decoder. The first path passes the data through 3 blocks of data compression and then 3 blocks of data decompression, while the second path bypasses higher level blocks after each of these steps. Each of these blocks consists of 2 one-dimensional convolutional layers, followed by a max pooling layer in the encoder and an upsampling layer on the decoder. On each level of the decoder, bypass data for that level is concatenated with the data from the main path before entering the convolutional layers on the decoder. For our model, we also built a multi-headed attention layer that is having a set of 3 attention heads for each operation or class. We have added it to the first encoding block, given that we will be using the entire period as input, and we want the attention layer to find the key action segments based on the occurrences found from the motif identification algorithm. The scores from the attention mechanism are then multiplied with the output from the second convolutional block and passed to the next encoding block and bypassed to the final decoding step. After the final decoding step, we have a submax fully connected layer that assigns the operation label to each of the time steps from the input sequence. As for the training for our network, we have the motif-guided attention training, where we use the occurrence sequence from the motif identification algorithm to guide the attention outputs of our model. As I mentioned before, Our model contains a multi-headed attention mechanism. Inside this mechanism, we assign a group of 3 attention heads to each operation. As you can see here, for each of these operations, we have a head in charge of focusing on finding one specific motif. So we have one attention head focusing on finding the unique motif, one attention head focusing on finding the supportive motif, and one attention head focusing on finding the boundary motif. During training, we seek to minimize the error between the attention head output and the corresponding motif occurrence sequence. So when the motif attention head and the unique motif for the read label operation is on training, it can be more aware of how to find the unique motif corresponding key action directly from the data. Besides the attention training, our network also trains its traditional classification loss and segmentation loss to better find the start and ending points of each operation. During training, the whole network is trained by combining all 3 loss values into a single loss to be used during the backpropagation calculations. Now I will proceed with the evaluation of our methodology. Our main test was conducted using the Logi dataset. This dataset contains 3 accelerometer data captured from the dominant hand of 4 workers inside a real-life logistics center. These workers perform a total of 267 packaging periods and have a varied skills of different ages and levels of skill. This dataset contains a total of 10 operation classes with a high level of data imbalances between them. As we can see on the right, operations like put on cart and using a pen have the minimal amount of instances, while operations such as picking and packing box take almost 30% of all instances inside our dataset. There are also some outliers, such as having worker 4 being the only worker that has an extra operation called attach address label, or worker 1 that does not have any instances of the parent operation. It's important also to note that given that we use a complete packaging period for our model as input, the high disparity between the average period duration caused us to modify the network size for each individual worker during our main evaluation. The second dataset tested to prove our method's capabilities is the LARA dataset, published in 2020 by the researchers from the Innovation Lab Hybrid Cybersystem Logistics at the TU Dortmund University. This dataset contains motion capture and acceleration data from 14 subjects performing logistics operations on 3 separate simulated scenarios. For our research, however, we only use acceleration data from the dominant hand from research subjects performing scenarios 2 and 3, since those scenarios contain the most similarities to our logic packing data operations. We, however, had to exclude subjects 11 and 12 since the small number of available working periods was not enough to actually get a result from our network. As we can see by looking at the classes available from this dataset, we can compare our method, how it performs, both recognizing simple operations such as the one on the LARA dataset and recognizing purely complex actions like the ones in the Logi dataset. Here is our evaluation methodology. We compare our model with these baseline models. We have traditional machine learning techniques, recurrent neural networks, convolutional neural networks, and we also tested our same network structure, but without using the Motif-guided training. That gives us thanks to the Motif-guided occurrence sequences. Here we have the parameters we use for evaluation. It's important to note that we use the best available motif length for each operation and each test case for each user or worker. As an evaluation method, we use the leave one period out cross-validation and the weighted average F1 score as our evaluation metric, given the high data imbalance of our datasets. Here we can see an example of a period output where we have the ground truth and the tested methods. We can see clearly how each of the methods performs on this graph. The LSTM-based methods can easily acquire continuous results. However, the accuracy of recognizing some specific or target operations is not there, while convolutional methods that focus on finding accurate restrictions for each data point have a harder time having a stable continuous prediction. Finally, we have the difference between our motif-guided training model and the one without it. While the motif-guided training model has some errors, we can see that most of the time it predicts accurately the corresponding operation. Here we have the lead one period out cross-validation for the logic dataset, which is our main test. We can see how our model continuously outperforms on each of the workers. It is important here to mention that worker 2 has the lowest prediction score, given that there is a high data imbalance as well as a lack of good data structure within his ability segment. We can mention from these results that we can outperform all other baseline methods by at least 15%, as well as traditional machine learning techniques by a good margin. As for the LARA dataset, we have the leave one period out cross-validation for the workers we selected. Here we can clearly see that the simple actions that correspond to the LARA dataset, although logistics do not have the same impact when compared to other baseline models. Each of these workers has, of course, a slightly better edge when compared to the MGANet result, but there's not a significant difference, which is why we believe our model has the best chance of usefulness when it is being used for detecting complex operations. Here we analyze the Motif contributions. We selected the result for each of these combinations of motif. We have the unique motif alone, both the unique supportive motif, the unique and boundary motif, and the boundary motif alone. Of course, while our full method outperforms the combination of different motifs, we have that the combination of the unique and supportive motif gives us the best result when analyzing motif contribution. However, the boundary motif by itself also has a high accuracy score, considering that it does not give any information to the model about which operation is being performed, only about the ending or start of each of them. Here we see how attention focus works on a period example. We can see how in the assemble box and read label operations, our attention value for the boundary motif can be clearly targeted to specific actions as well as results. We also see how the unique supportive and boundary motifs perform inside and outside the operations of interest, with really high scores inside the operation of interest and really low scores when being outside of them, proving the attention method is actually learning the overall location of our target operations. We also analyze the training data impact. Here we have the differences in data training using 20, 50, 80, and 100% of the total possible training data. In conclusion, we have that this study presents a new method for recognizing complex packaging tasks using body-worn acceleration sensors. We propose an attention-based neural network that proposes finding characteristic motions that help identify packaging work. And we tested our method on 2 datasets, a simulated one and a real-life environment, and outperformed the state of the art. We have that in the future, we will make public a dataset for human activity recognition in the logistics dataset. This new dataset called OpenPack will contain over 70 hours of packaging data based on a real-life logistics center instruction manual with multiple sensors such as RGBD data as well as physiological data. It will be soon available on this website. Thank you for your attention.